categories: parabolic, hyperbolic, and elliptic. Probably we started with
Yes, sir.
elliptic type. A health problem. For this reason, probably I could not continue more than half an hour today. So I will finish this lecture and stop. Actually, when we categorized our partial differential equation into three broad categories, we discussed about elliptic type. Poisson's and Laplace equations are the ideal example of elliptic type differential equation that involves a boundary. And we have our another class of equation called parabolic type and another equation hyperbolic. Parabolic type equations are sometimes called diffusion equations. Heat conduction equation is one of the examples of diffusion equations, and it is 30.1. This equation have some similarity with our electrical engineering eddy current problem. If we want to proceed with finite difference technique of deriving the numerical equivalent of this equation, what we need to do, we have to approximate the space derivative, the second derivative, and we have to find the time derivative. Actually, when we are discretizing our space, this is visible, but discretization of your time is not actually visible. It becomes an imaginary grid. Consider that in this figure 10.2, in 10.2, your equation is this. So you see that if this is your x direction, something is there in the x direction changing with respect to time. So your time grid is actually imaginary type. So in this direction, your imaginary time grid is drawn. Your I index for space and L index for time. So if you want to discretize or approximate the second derivative of a space, you have to fix a definite time. Then we use our finite difference scheme to represent d2 t dx2. Then in order to get the approximate the time derivative, we have to keep our space fixed. Then we have to approximate the time derivative for two time instants. So if this is done, then your equation will be taking the shape. And you see that all these algorithms are of explicit type. That means we will be calculating the new value with all the old values known to us. So you see a two subscript system is used here to designate your two types of if we examine this equation, you can see that your second derivative is approximated by using 3 points in a space at a particular time L. If the L index is for time and I index is for space. What does it mean then? It means that if our vertical imaginary grid is for time and horizontal is for space, then we are using, for example, these 3 points. If this is your I, this is your I plus 1, this is your I minus 1. This difference is del x. And in terms of time, this is your L. So at a particular time L, it is index, not exact time, okay? For example, if we have our L, like your I, J, K, something like this, okay? So if it is L, then L minus, say L minus 1 is 1 time step. That means the difference between 2 time step will be equal to del T. If we have another grid there, then this grid can be, if this is L plus 1. If we have another grid there, and that will be L minus 1. So say in this way, we have to discretize or approximate our derivative. So your second derivative in a space is obtained at a particular time L by taking 3 space points. Similarly, in your time derivative is approximated by using the difference of t in 2 time intervals. One is L plus 1, another is L. That means by using these two. So at a particular I, if you want to find the computational molecule, then you will see that you will have 3 grid points in X, I minus 1, I, and I plus 1. And you have your another point there. Okay, consider this is X. These two are used to approximate, just write the derivative dt, okay? Because this is your L plus 1, this position is L. And these 3 is used to approximate del t dx2. Our objective is what? Our objective is we have to solve for what? If we want to keep our position fixed, then we can merge in time to calculate the new values of t. And that new value of t will be equal to L plus 1. So we have to calculate either t I L plus 1. This is what the next time, the value of t at a space point I for the next time step L plus 1. Or if we want to keep our time constant and space variable, then our solution would be equal to t I plus 1L. One is the mass in time, another is mass in space. If we want to have a mass in space, that means we want to know how the quantity t is changing with time in different space point. Then we can fix our time and move to our space point and calculate the value of t. Then we again go to the next time point and again calculate all the things. And repeatedly we can keep doing and calculating the thing. So our solution is if we write our equation, then our equation will take this simple form. This equation is actually a march in time because you are marching in time, keeping your eye fixed. We are marching in time. So in order to do that, a constant will be there defined by lambda. That lambda is equal to k del t divided by del x square. And this is a crucial factor in determining the stability of the solution. We have to choose the value of lambda in such a way, or we have to choose our del x and del t in such a way your lambda will have a certain condition to be fulfilled. Then we will get our stable solution, or unless we do that, we will not get the stable solution. This is discussed there. So if we want to illustrate this by using an example, here is an example, okay? The example is nothing but a thin rod is there. The experiment to solve the temperature distribution of a long thin rod with a length of 10 centimeter with some constants are there. And del x is given, del t is given. At time t equal to 0, the temperature of the rod is 0. And the boundary condition are fixed for all times at T0 equal to 100 degrees Celsius and T10 equal to 50 degrees Celsius. Something like this. Okay, if you want to draw the figure, then you will understand what is the physical nature of the problem. For example, say we have a rod. That rod is 10 centimeter long. This is the starting end, x equal to say 0. This is your x equal to 10 centimeter. Then what is happening? The boundary condition means because you see the your equation has this form. If your equation has this form, that it contains a derivative dt by dx dt and also dt2 by dx2, then two conditions are to be specified. One is initial condition, another is boundary condition. So your boundary condition is defined as the temperature at the 0th position is given, and your temperature at the end of the rod is also given. So your boundary condition is there. Now at time t equal to 0, the temperature at any point on x at time t equal to 0 is given here as 0 degree. Okay, it can be different something. For example, if this rod in a room, then this temperature must be the ambient temperature of the room. Then how to just solve this problem here? Just we can easily, first thing is what we have to discretize this dimension. So here already del x is given. So we have our 5 sigma total. How many segments? 2, 2, 2, 2, and 2. That means it is 0, 1, 2, 3, 4, 5 segments are there. If we have the segments are there, unless it's tedious, it is rest. In this case, your k value, because in the equation, a k value is there, but by using some temperature or some, your k value is calculated to be this, and that with calculated your lambda is equal to 0.0 something. If this is your lambda, then our equation was equal to what? T I into L plus 1 is equal to TIL plus lambda into another set of factors there. Then we have to use this. Initially, when your time is there, then you at 0 time your everything is given. Then your next calculated position would be equal to what? Del T equal to 0.1. And that corresponds to L equal to 1. If we want to go to for next time, your delta equal to say 0.2. And that will be corresponds to L equal to something like this. So this is what the thing. For your time T equal to 0.01. In that case, this is the value T. What is that value? This is your, if this is your 1, your algorithm is equal to what? T L plus 1 I. In this side, this is equal to T L I. What is it? T L I is the previously calculated something or existing something. If we start with T L equal to 1, L equal to 0. That means this is the initial value. If you want to calculate for L equal to 1, then if this L equal to 0, then only when your second T would be equal to 1. So this is at time T equal to 0.01 second. And that will need the value of your temperature at T equal to 0 second. So this is the, because T equal to temperature at T equal to 0 second is nothing but the initial values. If our initial values are there, then we can calculate the next time temperature the next time by using this the equation already derived. Okay, so you can easily see what is happening there. So this is your earlier initial value. This is the value of lambda, and 3 nodes are involved there. If we have 0 node, we start from the left hand side, then we have another node there, we have another node. Because in calculating your D2T, dx2, you need 3 node points. This is your 0 node point, this is your 1, this is your 2. And initially, because the anterior node points are calculated to be in the previous time, our present time del T equal to 0.01 second, your previous time was 0 second. So in the previous time is the initial conditions. So the initial conditions of temperature at 1 and at 2 are all are 0. At 1, at 2, all are 0. Now at 0, that it is the left hand, the temperature was kept at 100 degrees Celsius. This is 100 degrees. Okay. So in this way, your T1 is calculated. So once your T1 is available, then we can go to the next point. Next point is 3. In this case, we have to calculate our next point temperature at time T equal to 0.01 second. And that will need what? That will need these 3 points. All these 3 points are in the previous time at 0 second. And the temperature of all these 3 points are actually the initial temperature. So the initial temperatures are there. So this is this. Similarly, for position 3, what you need to do, you will need this 3 point. If you will need this 3 point, then like the previous case, all the initial values are 0. Now we are going to the fourth position. If we want to go to the fourth segment, that will involve the rightmost segment. One of the thing will be the boundary. Then your boundary potential will be there. All interior nodes position is there. Okay, so these are the temperature now at T1. This is your T1, 1, This is a T11 means 0.1 second, and T21 means it is also in 0.1 second. T31 means it is also in 0.1 second, and T4 is also in 0.1 second. So your first calculation is completed. Now, if you want to go for your second time, you advance in time, then your index L will be changing from what to what. In your this calculation, your index was 0 and 1. In the next calculation, it will be equal to 2 and 1. So if we want to calculate our temperature at point 1, anterior point, in this case, your L would be equal to 2, and that is equal to 0.2 second. And that will need the value of your T1 at 1 plus lambda into the other factors calculated at T equal to 1. So this calculation is shown there. It is very simple to be understood, because your previously calculated value will be involved in your next time calculation. Then you have to repeat the thing. What is happening there? So at time t equal to 2 seconds, your calculation is repeated. You see that your previously calculated values are used there to calculate the values of your temperature at the anterior node points for the next time step. So in the same way, you can proceed in calculation. And if you just want to calculate this thing for many time steps, then you will say that your temperature at the nodal points are distributing in this way. Convergence and stability. What I have talked earlier, that if we want to have our stable solution for this implicit algorithm, this is what the inequality to be satisfied, 30.6. So usually your lambda should be kept less than equal to half. So if we satisfy this condition, you see that your solution will be stable. Now we will be considering about implicit method. Your implicit method is actually a complicated something. The reason is that in the implicit method, you will have some unknowns involved there in the right hand side, also in the left hand side. Your calculation molecule is shown there. You 30 in figure A of 30.7, you see that this is what the nodal points involved in approximating your second derivative of space and time, the first derivative of time that I talked earlier. For the implicit case, this grid will be taking this form. So you see that your time derivative will be calculated in this way. So if we want to find the implicit derivative grid to involve the space difference, okay, you see that the space difference is calculated at a time point that is L at L plus 1, not at L. So if we want to proceed in this way, then what will happen? Like your ordinary differential equation, you have to solve your simultaneous equation at each time step. Otherwise, a solution cannot be done. Okay, this is it can be understood by using this equation 30.7. You see, this second derivative previously was estimated as time step L. Now it is estimated at time step L plus 1. If it is time state L plus 1, we do not know yet the value of this temperature at time L plus 1. So what will happen then in both sides, left hand side and right hand side, we will have our time L plus 1. So in that case, what will happen then, your equation will take this shape, 30.8. If we have this equation with us, then what will happen then? For each time step, we have to, our objective is what? Our objective is we have to solve for time temperature Ti L plus 1. If we want to do that, we have to then obtain a set of simultaneous equations. Then if set of simultaneous equation will be there at each time step, then we have to solve. And again, we have to go to the next time step. This is best illustrated in this example. Okay. Then you see that at each time step, we will have a set of differential equation that you need to, the set of simultaneous equation you need to solve. This is very similar to what we have talked earlier about solving simultaneous equation using implicit method. At each time step, this thing is that as you know that your unknown will be involved in both sides, so you cannot uniquely solve it. For this reason, what will happen, you have for each of your time space step, after writing your equation, then we have to find the solution. Our objective is what? Our objective is what? We have to find the solution L plus 1 into I. This is what the thing we have to determine for each of your time step. If we start from our 0 condition, then this will be equal to 1, 1, another will be equal to 1, 2, another will be equal to 1, 3, another will be equal to 1, 4. All these 4 things we have to determine. Then what will happen in doing this, you will see that in both sides, this equation, this thing will be involved. We cannot solve by using a single equation. And what will happen then at each of the step space point, you have to write your finite difference equation. Then you arrange the equation into the form of simultaneous set of simultaneous equation. Then you solve for your temperature. Once this solution is made, then you switch to your next time step and repeat the process. Okay, then we will discuss about our some algorithms are there. These are actually a bit higher order algorithm. We will be skipping this thing. I will talk about the solution of parabolic equation, but not today, in the next day. And that will conclude the lecture of your partial differential equation. Then we have one topic left, introduction to optimization, that we will talk in the next day, inshallah. So that's it for my part today, because I am a bit sick, so I cannot proceed to continue.